Okay, so now we have 5.28 on week 5, and we're looking at steam that's entering a nozzle, and then it enters at 10 meters per second, and then it leaves at a given velocity that we don't know. It enters with this set of properties, leaves with this set of properties, and we're asked to calculate the velocity of exit, which I'm going to call V2, okay, and the volume flow rate at the exit, which I'm going to call vol, VOL, 2, with a little dot here to indicate its rate, right? So it's the rate at which volume 2 changes with time. So I'm just telling you that because it's going to be V per both. So velocity is going to be V, and then volume is going to be vol, okay? To be able to solve this, we're going to have to apply 2 principles. First principle is the mass conservation principle, which is going to state that the rate of mass on the inlet has to be equal to the rate of mass on the outlet. So the amount of mass that's going in is the same amount of mass that's going out. In other words, we can't have water of the steam accumulating inside the nozzle. Okay, and that's a very good approximation for engineering purposes. The second principle we're going to apply is the energy conservation principle. Energy conservation principle, which states that the change in energy, right, has to be 0, or just like the mass conservation, we can't create or destroy mass, we can't create or destroy energy. So whatever is the energy of the steam that's entering here has to be equal to the steam that's leaving there, and also this loss of energy that we lost due to losing heat at a rate of 25 kilowatts. Okay, so the energy over here has to be equal to this one over here and this one over here. Another way to write that is energy on state 1 has to be equal to the energy on state 2 plus in the energy lost. Okay, so I'm just going to denote for now as EL. Okay, so I'm just going to, so let's look at the situation here. Let's try to define this better. The energy on any of these states, we can break down this energy as, of any moving fluid actually, can break the whole energy, the sum of it, all the energies, the sum of energies, as pressure volume, right? So that's pressure energy of the fluid, the internal energy of the fluid, the kinetic energy, and the potential energy. Okay, so this is related to the pressure and the volume that any fluid occupies when it's moving, and the change is related to that movement. The internal energy are the energy of the molecules that are bouncing around. The kinetic energy is literally the energy of the molecules in terms of speed, velocity, and potential energy is the energy of these molecules from the ground, right? The energy they gain as they go away from the ground, from Z equals 0. Now, as long as our nozzle is not huge, that is, as long as there's no big difference between the molecules that's here and over here, and I don't know any nozzle that is huge to that point, we can pretty much ignore the potential energy on these nozzle situations. All right? So how can we write this down? If there's no loss in energy, right, if delta E is 0, then the energy on 1 has to be equal to the energy on 2 plus any energy lost. Okay, and then we can write this energy state here with these variables. So pressure 1, volume 1, plus the internal energy 1, plus the kinetic energy 1 has to be equal to pressure 2, volume 2, plus the internal energy 2, plus the kinetic energy 2, plus energy that was lost during this process. Right? So if you guys recall, this relationship here between the sum or the difference between internal energy and PV is precisely enthalpy, right? It's precisely the definition of enthalpy, H. Okay, so we can sub both sides by H, and then we can have a simplified version, which is H1 plus kinetic energy 1 has to be equal to H2 plus kinetic energy 2 plus any energy that was lost during this process. All right. Now, note that we have a power over here. So we have a rate change of energy, the rate of change of energy. So what we can do is we can take the integral, or sorry, the derivative in respect to time for the whole thing. Then everything is going to be converted into power, right? So that's what I'm going to do. I'm going to take the derivative in respect to time for all the things that we have, okay? But before I do that, let's just recall what these guys, let's write this in another way. Let's write this in another way. Big H, or that is just energy, can be written as small h times the mass, right? Because the small h is like specific enthalpy. It's the enthalpy divided by the mass. So we can write this as this times the mass. Kinetic energy we can write as the mass, velocity 1 squared over 2. Then enthalpy 2, same thing, small enthalpy times mass. And this also mass velocity 2 squared. And this guy here, I'm not going to change anything for now. Right? So I didn't change the whole equation, just broke this down into these two guys, this into this, this into this, this into this. And then I didn't change this guy. Now what I'm going to do, I'm going to derive everything with respect to time. Okay, so I'm going to do. So I'm going to have d h1m with respect to time plus d m, let's put the same way, m v1 squared over 2 with respect to time equals, push it this way a bit, there you go, derivative of h2m with respect to time plus derivative of m v2 squared with respect to time, and derivative of the energy loss with respect to time. The reason why I did this is because we have a power. It's given in the form of power, the energy loss, so now we can actually plug it in, because the rate of energy loss over time is the power lost, right? Awesome. Now, note that over here, this term here, this is the mass flow rate. So how the mass is changing with respect to time, that's the mass flow rate. So I can rewrite this whole thing. All these guys can become h1 times the mass flow rate, 1, plus v1 squared over 2 times the mass flow rate, 1. On this side here, h2 mass flow rate 2. There's no square, it's mass flow rate 1. There you go. And on this side here, I'm going to have my v2 squared over 2 mass flow rate. And over here, I'm going to have, now I have power lost. Right, so PL instead of EL now. Cool. Next thing we can do here is I can go ahead and I can divide everything by the mass flow rate, because since the mass flow rate, remember the mass conservation, because mass flow rate 1 equals mass flow rate 2, what I can do is I'll divide everything by mass flow rate. So I'll have h1 plus v1 squared over 2 equals h2 plus v2 squared over 2 plus the power lost divided by my mass flow rate. Okay? And another way to think of this step that we did from here to here, if you want to, if you're not satisfied, is to think that the enthalpy is not going to change with time. The enthalpy on state 1 is the same, right? No matter how time passes by, how much mass goes through, the enthalpy, as long as this is the same, is going to be the same, right? The velocity 1 is the same thing. The velocity 1 is not going to change, right? The velocity itself changes as we go through. The velocity 1 does not change with time, so it can come out of the derivative. Same thing applies for enthalpy on the second state and the velocity on the second state, right? So they're constants in respect to time. The mass does change, right? Because we have mass flow rates. We have mass that's going from one side to the other. Okay, so now that we have this savvy equation here, we can try to find the velocity 2. So to find the velocity 2, the things that we need to find to be able to solve for this guy here is we need velocity 1 that we have. We need enthalpy difference that we don't have yet. We're going to need a mass flow rate and the power loss we do have. So we need to grab the two enthalpies and the mass flow rate to be able to solve this fella. I'll start with the mass flow rate. So if we have the cross-sectional area, remember it's 800 centimeters squared. So we can use that to our advantage because we know that It's right down here. We can grab a volumetric flow rate by multiplying the velocity and the cross-sectional area. So in this case, it's going to be the 10 meters per second times the 800, and I need to convert that into meters, right? So I can do 1 meter is 100 centimeters, and I can square that. Okay, so I can cancel these out, and I'll have meters squared over there. Okay, so my volumetric flow rate will be 0.8, and that's going to be meters cubed per second. Okay, so now we have a volumetric flow rate, and then we can relate this to our specific volume, right? Because if we have two things, we have everything for that state. Okay, so we can go ahead and use this to find our mass. So let me change pages. Okay, so we're back, and check it out. We have, let's see if the focus is good. There you go. All right, so we have the volumetric flow rate, and we know that the specific volume is just the volume over the mass. So that means the mass is equal to the volume divided by the specific volume. So if we take derivative with respect to time on both sides, we're going to have dv dt 1 over specific volume. Okay, so we have this guy here. It's the same thing as this guy here, right? And we just need to grab the specific volume, and I can do that on the table. We're talking about water, so we go to table A6, and on page 908, and I'm going to grab specific volume for this, what is it, the 400 Celsius and 800 kilopascals, and I got 0.38, 429. Okay, so my mass flow rate, or m dot, equals the volume flow rate of 0.8 divided by 0.38429 meters cubed per kilogram. So left of kilogram per second, which is precisely the unit for mass flow rate. So I got, what is it, 2.08 kilograms per second. Okay, so we killed one of the things that we needed to find, killed that task. And don't forget that this is both mass flow rate 1 and mass flow rate 2, right? Because of the mass conservation principle. Okay, so now we need to find the difference in enthalpy. And there's two ways you can do that. You can go to the tables. Let's close this bracket down. Let's close this bracket down. There you go. So we need to find delta H. So there's two ways to do it. You can go to the table, grab H1 and small h2, or you can use CP, whatever rocks your boat. Okay, I'll do CP for this one. So we know that delta, small case enthalpy, will be the CP times my delta T. I have the delta T. So if I go to the table to grab my CP, I'm going to grab, I have the difference in temperature. So my delta H is going to be, let me just check. Oh, never mind. I'm not going to do this one. I'm not going to do CP. I'm going to do the table one. My bad. So I'll get H1. From the table, I've got 3,267.7 kilojoules per kilogram. You're welcome to do the other way. If you want to use this way, fine, up to you. And the other thing you need to be notice is that on state 2, we're actually going to have a superheated state. It's not going to be a saturated state. We look at that. You know how to do that already. If you don't, leave a comment and we'll talk about that in detail, but you should by now. And if you go to the right table, which is superheated at 0.2 megapascals, I got 3072.9 0.1 kilojoules per kilogram. Okay, so I did it from the tables. So that means that I can now grab my delta H, which will be H2 minus H1. And that's going to be given in kilojoules per kilogram, which is precisely what we're after, right? And so we have the mass flow rate that we needed. We have the delta H that we needed. So I think we're good to go. Let's go back to our main equation, which stated that, just recall that where we came from, right? We were looking at this equation here so that we could solve. So we needed H1, needed H2, and we're trying to find this guy here, okay? So let's actually write the whole thing down and then we can go from there. So H1 plus V1 squared 2 equals H2 plus V2 squared over 2 plus the power lost divided by the mass flow rate. Okay. We're after this guy here, so I'm going to say that guy, so I'm going to have V2 squared over 2 will be equal to V1 squared over 2 plus, what's the difference here? Well, it's going to be H1 minus H2. Okay, so it's the inverse of what we generally get, okay, because we're after velocity 2, so it's going to be V1 minus H1 minus H2. And then the minus power loss, mass flow rate. I can multiply everything by 2, so I'm going to have that my V2 squared equals my V1 squared plus 2 H1 minus H2 minus 2 times my power lost, my mass flow rate. Okay, for all this to make sense, don't forget the units here. This has to be joules per kilogram, joules per kilogram, joules per kilogram, joules per kilogram. This has to be joules per kilogram as well. So when we plug in our values, we need to make sure that we have the right units, right? So V1 we have, that's 10 squared plus 2 times. We have these guys in kilojoules, so we're going to have to grab this in joules. It's going to be 10 to the times 10 to the third, right? We can write this down if you want to over on the corner. Let me just grab my calculator. Okay, so watch out because I'm going to flip these two. So my H1 minus my H2, okay, will be, let's see, it's 3072.1 minus 3267.7. That's going to be 192 positive 195.6, right? That's kilojoules per kilogram. So that's the same thing as 195.6 times 10 to the third joules per kilogram. Make sure we have the right units. So that's going to be 195.6 times 10 to the third. And over here, same thing. We have kilowatts, so it has to be in watts. So it's going to be 25 times 10 to the third divided by our mass flow rate, which is 2.08. Okay, so then we can take the square root over there, and we get that the velocity is, where is it? Velocity is 606 meters per second. Okay, so we got a big boost in velocity. We go from, is it 60 folds in velocity boost. And then the last part is quite trivial, right? Because we can grab the specific volume for the second state, again on the table. And we noted from the previous work that we did that if we have the specific volume, and the specific volume for this case is 1.31623 meters cubed per kilogram, and we have the mass flow rate, which is this guy here, then our volume flow rate becomes trivial, right? Because we can do the same process that we did before. Right? If we want our volume flow rate, So d vol divided by dt, that would just be our mass flow rate times the specific volume. So it's going to be 2.08 times 1.316, and that's going to give me approximately 2.74 meters cubed per meters cubed per second. Right, so it's meters cubed over kilogram times kilogram per second, so that's meters cubed per second. All right, so that solves it for this one. Let me know in the comments if you have any questions, or send me emails.